Hello, everyone. Now, I'm Charles, and today I'll be talking about our work, which is titled Trace Partitioning as an Optimization Problem. And this is joint work with Matthieu Lemerre and Sébastien Bardin, and Jean-Yves, Marion. And okay, so there are several sources of imprecision in static analysis. And where does imprecision come from? Firstly, like not using best abstract transformers, and secondly, primarily due to incompleteness of best abstract transformers, and thirdly, using the abstraction itself when it's not precise enough to prove properties, and fourth, like when composing the abstract operators, you also have imprecision, and fifth one, primarily what we will be focusing is more about the non-distributive domains where joins also inject imprecision in the analysis. So how do you solve the imprecision? The well-known idea is to develop more precise domains or more transfer functions, but you know, it's really quite challenging because people spend a lot of years developing good domains. And the other approach is trying to use generic method based on trace partitioning, which I'll be talking about today. So here is a code, which on the left you can see, where x is modified in two different ways. X is equal to 1 and x is equal to -1. And you want to assert in the end that x is not equal to 0. So if you just use plain interval analysis, when the results are joined after the conditional statement, you get -1 to 1, and then so you no longer can prove the property. On the other hand, if you take the partition state where you keep the values of x separate, where you have x now no longer contains 0 in it, and now you can easily assert that x is not equal to 0. So unfortunately, there are two problems with trace partitioning, where when you have too many disjunctions, this leads to path explosion. You see the program on the right, where you have sequence of conditionals, and if you split too much, this leads to path explosion. And the second problem is if you use too few disjunctions, you may not improve precision. It's the same program between if then else and assert. I added some unnecessary code. And if you just use interval analysis, and of course, like when you merge the value of x, you will have -1 to 1, and so you can no longer prove the property. But on the other hand, if you use the partition state, where you split for some time, and if you don't know how long to maintain disjunctions, and if at some point you merge the analysis, you get x from 1 to 1, and again, you can't prove the property. So if you use too much, you lead to path explosion, and if you use too little, you may not improve precision. So the classical method for trace partitioning is to use heuristics to obtain some trace partitioning that balances, you know, like trying to improve precision, but not leading towards path explosion. And the question we ask is, how do you find suitable trace partitioning that improves precision and avoids path explosion? So the main contribution of our work is to develop a search-based method to find an optimal trace partitioning. And there are couple of contributions here. One is we do search-based quotienting, which I'll talk about a little bit later. And then the ratchet search about continuous improvement of precision. And thirdly, incremental computation. And fourth, we'll talk about dealing with non-monotonic operators and also the lessons learned. OK, I'll motivate with an example. Here you have the program on the right. And we want to use analysis like using constant propagation. Here you have two variables, x and y. And you have an error location, which is, although not reachable in the concrete, it is, the analysis says it is reachable in the abstract, where you have x and y as top, like you can see in the bottom. So the program is, we did not prove that the program is safe. And let's say if we do make some splits in the bottom, as you've seen here, we do improve precision. Now the precision at the error location improved from top to 1 to top, but still it is not enough. Let's make some more splits like I've done here. Now we managed to get the bottom state at the error location, and that we proved the program is safe. But we asked the question whether it is optimal. In fact, it is not optimal because now we can undo the split that we have done before, and you still maintain the same fixed point state at the bottom at the error location. And now the program is safe. So you saw an observation here is that if some new splits can make older splits also useless. And so as you've seen here, we have this, for the original program, there are several refinements. Some improve precision. Among them, some improve properties. Among them, some are more optimal. So how do you find these optimal refinements? Given that the search space of possible refinements of the original program is quite large and mostly graphs, like searching among the graph is quite hard. So the first contribution of our work is how do you quotient the search space, and we do it with using tuples. What are tuples here? So take the program on the right, and here we a priori select some split points, which I highlighted in star, which has multiple incoming edges, and which we want to separate. And now we take it, so since we selected 3 points, we have 3 tuples, where the dimension is 3. And we associate each dimension to a split point. And now, since we have tuples, there are certain operations we can perform on tuples, which are, for instance, successor operation, like I will do here. So if you apply successor operation on the third component, you get 0, 0, 1. This exactly corresponds to, this successor operation has a corresponding delay operation for the third split point. As you can see, I delayed the third split point by 1 step here. So, of course, it did not improve the precision. It's the original example itself. So we'll try with more splits. And here we can go from 0, 0, 1 to 1, 0, 1, where I'm now applied successor operation in the first dimension, which means I will be delaying the first split point at the top, which now says that the error is unreachable. And finally, because it is not optimal, then we again undo the successor operation that we did at the third dimension, and we go from 101 to 100, which means we have a corresponding merge operation on the graph, and the program is optimal now. So what we have shown here is that in the paper we show that there is a homomorphism between these n tuples and the CFG refinements, and more details are in the paper. And in fact, because searching in the graph space is quite hard, and now we can do it in the space of tuples, which is much easier to deal with. And so tuples provide an approximate measure of precision in the graph size. So if T1 is less than T2, then in fact the HT2 is kind of a refinement of HT1, and which means you refine HT1 itself, and the program size is also a bit larger. And when you do fixed points, when you compute fixed points on the HT2, and it is at least as precise as HT1. A small caveat here, we assume that abstract operators are monotonic, and we'll talk about non-monotonic operators a bit later. And an important observation is that if T1 is less than T2, it means that the graph corresponding to T2 is strictly larger, but possibly equal in precision. So this leads us to something called this is two-phase search, where in one phase we can improve precision, and in the other phase we can find a minimal program which has an equal precision. So you can see that in the picture on the right. So when we improve precision, we are making some splits, which means we are this is the precision axis, and that is a program axis. When we improve the precision, we are going up in the program size as well as in the precision axis. And then when at some point, when we go to the minimization phase, we try to maintain the precision, whatever we had before, and try to shrink the program size using the merging. So, and you do this in alternate phases, and then you improve, merge, and you improve, minimize, and so on. This is the trajectory you get on in the search space. And this is how we do the search to improve trace partitioning. And the algorithm is anytime, because anytime you have, if you're satisfied with the precision you have, you can terminate with that particular refinement. And what does equal precision mean here? Because when we have some set of, when we have two refinements in the search space, what does it mean for them to have equal precision? Here I have the same example, but I removed the assertion and added some useless code. Again, if you do interval analysis, x will be -1 to 1. And on the partition side, if you try to keep the value of x separate, but you see that I kept it separate until the end. So you can see that splits do improve on useless control locations, but it's not something we don't want, because a fundamental insight of our work is that we aim to improve precision at some locations of interest. For instance, these are assertion points these are, for instance, locations which have unproved assertions. And the important consequence of selecting few locations of interest is that whenever a split is no longer contributing at the locations of interest, we can now merge it. So that's what I've shown in the earlier example, where the split is no longer contributing at the error location that I managed to merge it. If we try to improve at every location, then what ends up happening is we go up in that, we never come down, and we just keep going up and up, and we go to path explosion. And when we are traversing the search space, going from one refinement to the other we should not do like, okay, when we're going to the other refinement, we don't want to compute the whole graph refinement from scratch, and don't want to do whole fixed point computation on top of it, because it's quite expensive. How do we mitigate this? We use incremental computation. For instance, when we do a transformation, we are just locally changing the graph at few points in the program, few control locations. So these transformations are imperative on imperative graph, and now we just only remove parts of the fixed point map where we have to recompute, and we don't have to recompute for everything. So you can see I just dropped 3 states here, and then I can recompute them like this. And then, okay, when we apply another split, we just locally change the graph, modify the graph a little bit, and then we recompute the states again there, like this. And when we go there, we don't have to recompute the other states on the left, because the state at 3 did not change. So the only state changes that I need to do are on the right-hand side, because the state at 8 changed, and so we have to update this one, and then this one, and then we prove that the error is unreachable. So this is what incremental computation allows us to, because it's very cheap in nature, so it allows us to test several thousands of refinements in seconds. And another one is the tuple exploration strategy to improve precision. First one is pruning. Let's say if a tuple 3, 4, 2 is not improving in precision, then we can in fact, we don't have to explore all the tuples which are smaller than that tuple itself in component-wise ordering. So, which means we prune all the downward closed elements of that tuple. And next one is the priority exploration. And one of the insights is that it's important to explore one dimension at a time first, because firstly, this has a smaller search space, because now you don't have to do like trying to improve 2 dimensions at the same time, or 5 dimensions at the same time, or 10 dimensions at the same time. But improving 1 dimension at the same time is actually enough. And for the programs which do require multiple splits, what we have observed is the following. So let's say there are 2 splits, and at the locations of interest you have precision D. And let's say you make a split here, and it in fact improves, let's say it improves D prime. And since it improved at locations of interest, we keep that split no matter what now. And then let's say we do another split, it does further improve to D double prime. So for the programs which do require multiple split, we can in fact get through, we can actually get there by just sequentially exploring the dimensions. And this actually reduces search space significantly. And finally, we also have to address non-monotonic operators. Let's say you have the program on the right, just don't have to focus on it. And there is let's say, previous refinement, and then there is a current refinement. And let's say basically the current refinement you obtain by splitting somewhere, which happens at which happens there, which I'll show. Just focus on the states which are in color. So in the previous refinement, x is 1 to 160, 1 to 60, and when we make a split, x becomes 1 to 1 or 60, 60. And actually see that now the abstract state of the loop head completely worsens compared to what we had in the previous refinement. Okay, doesn't get worsened, but it becomes completely incomparable. Previously you had minus 40 to infinity, but now you have minus infinity to 1. So because we are trying to monotonically improve precision, non-monotonic operators are a bit tricky because the current refinement can have really incomparable precision with the previous one, or the worst precision even, for instance. So how do we solve this? Instead of a naive solution is to basically discard the current refinement and just focus on the refinements which lead to better improvements. But in our work, what we try to do is we have a nice trick called forcing monotonicity. So these two states, as you can see, minus 40 to infinity and minus infinity to 1, they're in fact sound approximation of reachable states themselves. So what we can do is, in fact, we can take a meet of them. Meet is, in fact, even a sound approximation of reachable states. And then we can force that new result in that current refinement. Now, in fact, that this becomes much better. In fact, we improve the loop invariant itself there. And this is how we do, this is how we force when you have non-monotonicity doing some tricky things. So to summarize, when you have monotonic operators, incremental computation, when you incrementally arrive at a refinement, it yields same results as doing whole fixed point computation on that refinement. But when you have non-monotonic operators, incrementally arriving at a refinement can yield at least as precise or even more precise than doing whole fixed point computation on that refinement. So, and the invariance that you get by doing incremental computation really depends on the exploration path taken. Because these invariants may not be inductive, or may be inductive or may not be inductive, so how to reproduce them? You take the exploration path and you can reproduce those invariants. And finally, we have the evaluation where the analyzer is written in OCaml, and we use SV-complete safety benchmark with programs and its details on the paper. And as for the domains, we use Aptron library and we don't implement these famous domains from scratch again, and we just use the library, and then we also add constant propagation and the product of intervals and congruence. So conclusion, it's actually, so on the x-axis you have the number of property instances, on the y-axis you have the computation time. For each program we give like 1 hour timeout. And we have three baselines. One is the no split, where we do not do any trace partitioning, and full split, where we do full trace partitioning with k is equal to 1000. And the usual heuristic, which tries to split everything incrementally, is what we use for third baseline. And our primary algorithm is IDDDS, which is kind of iterative deepening depth first search based algorithm, and it outperforms. It proves a lot more properties, and these baselines time out, like at least no split and full split time out quickly on a lot of programs, and it's also much better than the standard heuristic SDS. And on the other side, on the next one, we have that the approach is agnostic of the domain, where we take these 4 domains, which are mainly taken from Aptron, and we add constant propagation. And basically, as long as the abstract operator implementations are given, which is just widening or inclusion or join, just basic operators, and you plug in and you can use the refinement. So as you can see that these domains, and as you can see, like a lot of these domains do much better with trace partitioning than without trace partitioning. So, and other one is we have incremental computation. We show that incremental computation is actually quite useful, and that it really outperforms the non-incremental for the programs at least, which it can get. It is worse in terms of the number of transfer functions computed. So that is, y-axis is the number of transfer functions computed, and the x-axis is the property instances solved. And incremental one outperforms by 100 times, and for the programs which non-incremental gets, and even non-incremental times out on a lot of benchmarks. And finally, we also have a combination of different sensitivities, where we take, in this paper we have implemented 3 tuple encodable transformations. One is joint splitting, and other one is loop unrolling, and other one is context sensitive. So each dimension can be any of these 3 things. And in fact, we showed that combining different kind of transformations proves significantly more properties than using a single kind alone. And finally, to conclude, we tackle the challenge of automatically tuning the phrase partitioning by casting it as an optimization task, and we provide a search-based method to solve it. And I think it's quite useful and quite easy to plug in any existing static analyzers and to improve precision. And it is available as an artifact. Thank you.
Thank you for your talk. We have time for any questions.
Hi. Maybe I missed something, but can you motivate your pruning again? Because it seems like you've already done the analysis with the split graph. So why do you want to prune it? I mean, you've already done the analysis. Or is it something where you're analyzing the same function again and again, and you preserve the split?
Oh, let's say when we have explored the tuple 342.
No, it's not this one. You had this other graph where you were talking about the program size and the that one, and then you sort of unsplit, right? You
here
you merge, yeah.
So when you do go up like this, you split, you perform transformations, and then here you undo the splits.
Right. Why?
Because if you don't, then you keep going towards, you go up and up and up, and you go to path explosion, which is something that you don't want in the first place.
But how do you decide?
So this is what I've shown in this example here, right? So when you merge this branch and you recompute the state again, you will end up having the top, you will end up having the bottom. So it's incremental. So you merge, you try to merge and see what you get, the result. And if you end up having the same result, which means you can merge it, yeah.
So sorry, so the precision that you're measuring is some sort of local, like you're unsplitting or merging to maintain some local precision.
Yeah.
And okay,
sometimes it can be like this. For instance, your location is somewhere.
Right.
But let's say when you merge, it may worsen the precision. But
right.
When you propagate that, you can end up having the same one too, at the locations of interest. So what you care about is the precision at locations of interest. Here, the location of interest is this one itself. So when you merge, you check the result here, and it's the same top. It's the same bottom.
Right. I think so my question was, I think, answered.
Okay.
So we've been talking about merging, and I'm sorry to go on about merging, but in the paper, you mentioned that the merge function rarely runs. Like, you rarely find a tuple that actually maintains precision and reduces the size. Do you have an intuition for why that's occurring, or why there isn't some equivalent smaller graph?
I think my intuition of it is that when you have locations of interest, which is quite small, like if just one location here, usually when you have a lot of locations of interest, that's when you will really need merging. But if you just have very few locations of interest, merging is usually not useful, but I can give you more details about it.
If you push partitioning to the extreme, you get model checking. That is, you get all paths one by one.
Yeah.
And so I understand you have two ways to avoid it. That is, first you choose the tuple.
Yeah.
How is all points where you have a choice, or you have
Yeah.
some heuristic? No, all points.
So no. So at least in the experiments, we selected all the points which has multiple incoming edges, and then you can extend the tuple to even, you can dynamically add new split points into the tuple too, because you now start with a 0. That's
Okay.
it. Yeah.
And the other way to avoid this explosion is the undo,
Yeah.
and that the only two things you need.
Yeah.
Okay, good. Also, it's exponential or tower of exponential, the time.
What time?
The time that it takes to do the partitioning, I think it could degenerate in some exponential or even tower of exponential time.
Yeah.
Because the experiments are nothing, because an experiment is always constant time.
Yeah. Sure.
So
Yeah. So let's say if your property itself needs full path explosion, then there's nothing you can do about it.
okay.
Yeah. But if you don't, then if you have an optimal trace partition which can prove the property of interest, you can necessarily find it.
So I was thinking you need some kind of widening in this process somewhere.
Widening. I haven't thought
The
about
point
that.
where you decide not to go further in the partitioning.
Maybe we can discuss it offline. I can't think of an immediate answer.